Section 5.2 deals with bisectors of triangles. Today we're going to talk about two different types of bisectors, perpendicular bisectors and angle bisectors, and how, when they intersect, they form specific points within our triangle. So the first one we're going to deal with are the perpendicular bisectors. Now, as a reminder, perpendicular bisectors are lines or segments that intersect other segments, and they form right angles along with splitting that one segment into two congruent segments. So perpendicular bisectors, when they intersect in a triangle, they're going to form a point, and we call that point a circumcenter. So the circumcenter of my triangle, which in our theorem down here would be point P, is where all of the perpendicular bisectors of my triangle intersect. So notice the red line segments we have here are my perpendicular bisectors, because not only are they forming a right angle, but they're also splitting this segment into two congruent parts. Same thing happens over here. I've got a right angle, so we know it's perpendicular, and I've got my two congruent segments. Last one, right angle, so I know it's perpendicular, and I've got my two congruent segments. So these red segments are my perpendicular bisectors, and when they intersect, they form this point called P. Now this point P has something special going on with it. With this point P, there is a theorem called the circumcenter theorem, and that theorem states that if I were to take a look at from point P to point A, that distance that I get from the circumcenter of the vertex is actually going to be the same exact distance as it would be from point B to P, or from point C to P. So in this case, anytime you're dealing with a circumcenter, the distance or the length of the segment from my vertex to the circumcenter is going to be the same in all three instances. Now, some side knowledge is the circumcenter can actually be found either within the triangle, on the outside of the triangle, or actually on top of the triangle, depending upon the different types of triangles you are utilizing. So if I'm dealing with an acute triangle, all of the perpendicular bisectors that I have will intersect and form the circumcenter on the inside of my triangle. But if I'm dealing with an obtuse triangle, notice the obtuse angle here, my perpendicular bisectors, when I make them on my triangle, are going to end up intersecting outside. So the circumcenter will be on the outside of an obtuse triangle, and in a right triangle, my circumcenter will actually sit on the triangle itself. So for the first example we're going to take a look at, we've got the triangle ABC. And in this triangle, they're telling me something very, very important. That segment DG, EG, and FG are all perpendicular bisectors. So DG, EG, and FG are all perpendicular bisectors, meaning that point G is my circumcenter. And remember what I said about circumcenters. The circumcenter then says that the distance from that circumcenter to the vertex is going to be the same distance no matter what vertex we're using. So AG, BG, and GC are all going to be the same. Now, this question asks us to find what GC is for the length of the segment. So if I'm looking for GC, I'm noticing that GC is this segment right here. Now, that goes from the circumcenter to the vertex. So if I'm looking at the diagram, I notice, well, I don't have this one labeled, but I do have BG labeled, and it's labeled as 13.4. Therefore, GC is 13.4 because the distance from my vertex to my circumcenter is going to be the same no matter what. So if you had to explain that, possibly in your homework, you might end up getting a question where you have to explain such. You'd say if segment DG, segment EG, and segment FG are perpendicular bisectors of triangle ABC, then G is the circumcenter, making it equidistant, meaning the same distance, equidistant from the vertices. Therefore, remember the three dots means therefore, if BC is 13.4, so is GC. So if you have to explain it, that's how you would do it. So let's go ahead and take your knowledge of circumcenters and perpendicular bisectors and put them to good use. In this example, they're telling you that KZ is a perpendicular bisector for my triangle GHJ. What I would like for you to do is I would like for you to try to find out what the distance for GK would be and the distance for JZ. So take a look at the diagram, try to figure those two out for me, pause it at this point in time, and when you're set and ready to see what I've got for answers, go ahead and start the video up again. So let's take a look at part A. It says find GK. So if I'm looking for GK, GK is right here. Now, we know that KZ is a perpendicular bisector. So if it's a perpendicular bisector, not only does it give me a right angle, sorry, I'm trying to make a right angle, also, I know it bisects that segment, so that KH and GK would end up being the same length. So if KH is 18.6, that means that GK would be 18.6. Now for JZ, they're talking about the distance from J to Z. We're dealing with the line segment that goes from the vertex to the circumcenter. That means that would be the same distance from Z to H or the same distance from Z to G. Now, since we're working with Z to G, and that's the only one that's labeled with this 19.9, I know that JZ should also be 19.9. So now that we've talked about perpendicular bisectors, we're going to add in the other type of bisectors. We're going to talk about angle bisectors. Now, angle bisectors in a triangle, those are the ones that split the angle into two congruent angles, so it could be a ray or a line. What happens is, if you take the angle bisectors of each vertex of a triangle, those angle bisectors will actually intersect each other, and they form a point that we call the incenter. So, for perpendicular bisectors, we get the circumcenter, and for angle bisectors, we get an incenter. So if we take a look at the diagram down here, notice that angle A, we've got this red line segment, and this red line segment represents my angle bisector. So I've got two congruent angles. Same thing happens here with B. The red line segment is my angle bisector, so it forms two congruent angles at B. And the same thing happens with C. I get two congruent angles. When that happens, all three of these angle bisectors end up intersecting each other at this point, and this point is P. That's what we call the incenter. Now with incenters, what happens is you actually end up having segments PY, PZ, and PX. Now those segments are actually going to be the same exact distance. So on the other one with the circumcenter, the distance from the circumcenter to the vertex was the same. In this case, the distance from the incenter perpendicular to the sides are going to be the same exact length anytime you're dealing with an incenter. So PY, PZ, and PX are all the same length. So unlike a circumcenter, the incenter will always remain on the inside of the triangle. So it doesn't matter if you're dealing with an acute triangle, an obtuse triangle, or a right triangle, all of the angle bisectors will always intersect on the inside of my triangle. So my incenters are always located on the inside of my triangle. So let's run you through an example. I've got MP, that line segment, and line segment LP are considered to be angle bisectors for this triangle. So as soon as I know I've got angle bisectors, I'm actually going to label them. So they said MP, which is right here, I end up getting an angle bisector. It's an angle bisector. So those two angles are congruent. And then they said that LP was an angle bisector, so I also know that these two angles down here are congruent. So now we have that. The first question A asks us for the distance from P to segment MN. And we know from before that the shortest distance from a point to a line, MN, is the one that is perpendicular. So I'm going to go ahead and I'm going to draw in a perpendicular line segment. So that's my perpendicular line segment. What I want to do is I want to find out what the length of this is. Well, in order for me to figure out what the length of this is, we know that since these two, MP and LP, are angle bisectors, they intersect at the point P, which means P is my incenter. And if I have an incenter, I know that the line segments from the incenter perpendicular to the sides are going to be the same length. So if PQ is 5, that definitely means that the distance from P to the line segment MN will also be 5. Next, when they're asking for the measure of angle PMN from P to M to N, I'm looking for this angle right here. So in order for me to figure out what this angle is, I have to do a little investigative work. I know that they're in the whole entire triangle, we have 180 degrees. Currently, 20 of those degrees are already taken up by the angle at N. However, at L, it's not just 50 degrees for the whole angle. We know that since this angle is 50 degrees, that means that angle QLP must also be 50. So if this angle is 50 and this one's 50, that means the whole angle at L is 100 degrees. So right now, I've got 100 degrees, I've got 20 degrees, and I've got to figure out what this whole entire angle would be at M. So if I'm thinking about it, there's 180 degrees in a triangle, 120 are currently taken up by those two. That means that I should only have 60 degrees left to be able to put at the entire angle M. So if the entire angle M is 60 degrees, that means each part at angle M should be 30. So the measure for angle PMN is 30 degrees. Since this example is pretty similar to the last example we did, how about you try it on your own? So once you go ahead, pause the video, and when you're ready, start it up again, and I'll have the answers written down, and then we'll discuss what happened. So I'm hoping A, you ended up getting 19.2, and for B, you got a measurement of 104 degrees. Let's walk you through it. So the first question asks you to find the distance from X to segment PQ. Well, they were already telling me that segment QZ, or QX, and RX were angle bisectors. Before we get going on that, let me go ahead and mark my angles so I don't forget that those were angle bisectors. So I've got congruent angles. Now, if I've got congruent angles and I want to find the distance from X to segment PQ is over on the side here. The shortest distance would be the one that's perpendicular. Now, with an in-center, we know that the distance from the in-center that's perpendicular to the side is going to be the same no matter which way you go. And it just happens to be that we know that from X to Y, it's 19.2. Therefore, from X to segment PQ, it should also be 19.2. For part B, we have to really look at what the angles are. So if I noticed here, I noticed that angle R was split into two congruent angles. So one of them is 12 degrees. That means the other one would be 12 degrees. So if the other angle here is 12 degrees, that means the whole entire angle at angle R is 24. The whole entire angle at angle P is 52. So if I'm thinking about this, I know that if I took 52 degrees and 24 degrees and the measure of angle Q, I should end up getting 180 degrees in my triangle. So I would have 76 plus the measure of angle Q would end up equaling 180. So the measure of angle Q is 104. Now, pay close attention to what the question is asking you. If they're asking specifically for PQR, PQR in this case is the whole entire angle, which is why we put 104 degrees down. If they would have asked for measure of angle PQX, I would have taken the 104 and divided it in half. So hopefully this makes sense. If you got any questions, go ahead, write them down. Make sure you ask in class. And don't forget to do your whisk.